Hi, nice to meet you in person.
Nice to meet you.
Good to see you.
Good to see you.
Hello, it's 4 p.m. We are going to get started because we have a jam-packed agenda this time with really interesting research talks the whole time. So I'm Dave Oren. I'm one of the ICNRG co-chairs. Rio Yanagida is I guess I'm his other co-chair. I managed to get him to do most of the work to set up for this session, so that's really nice. He's replaced Dirk Kutcher, who has moved on to more administrative tasks, and who is in the room. All right, so this is the ICNRG, and we are an IRTF working group. So just recall that there are intellectual property rules around participating in the IRTF, and you should be aware of those rules if you work in an environment that is cognizant of those things or have them yourself. We make audio and video recordings of these meetings, and in fact, we now have transcripts that can actually be processed by some tools that have come along. So be aware that anything that you say, do, or otherwise work around will be on that recording, or maybe. We have a privacy and code of conduct. If you're not familiar with it, please take a look at it. Those of you who have been participating for a while should be familiar with that. The IRTF is not the IETF. We do not do standards. We help organize various forms of the research, various parts of the research community, and provide a forum for interchange of ideas and presentation of research work for feedback from the community. We publish informational and experimental drafts through the normal publication process, but do not do standards. Some tips, please, any of you who have not used your capture to join the Meet Echo session. We track who are the participants in all sessions through that tool now. We used to use pieces of paper, believe it or not, so not that long ago, but now have those tools for maintaining the list of people who are participating. Our administration stuff, if you need pointers to things, the mailing list you should join, even if you don't follow it that much, and our data tracker webpages are available through the IRTF. Do we have a note taker? We have asked for a note taker, and if you may not want to believe this given how tight we are on time, but we cannot proceed unless somebody puts their hand up and says, I will take notes. The notes do not have to be very extensive. You don't have to write down what people are saying in their talks or anything like that. It's all captured. But for capturing a written form of some discussion questions and answers, we need a note taker. Thank you. Ali Bagan has agreed to be the note taker. Now I owe him doubly. All right, so here's our agenda very, very briefly. We have 1, 2, 3, 4, 5, 6 research talks. We'd like to keep to very close time. Most of them have 20 minutes, which means you don't have 20 minutes, you have 15 minutes to do the talk, and 5 minutes for Q&A. And we're going to hold people to that because every one of these talks is fascinating, and we don't want the later people in the session to be tough for time. In terms of the active drafts these days in ICNRG, there are a number. I just want to point out a couple. The CCNX chunking draft went through last call in the research group. It went up to the IRSG. It got an IRSG review. There were some comments sent back. The authors have reissued the draft with the changes. And it's at the moment just waiting in the queue for some administrative stuff to go back and make sure that the person who reviewed it in the IRSG is happy with those before we can move it to final publication. There's a versioning draft, which is an active RG document. We're waiting for more comments on it. We would like to get it to last call sometime, hopefully very soon. but we haven't gotten enough feedback yet to do that, and we'd like to do that. And lastly, there's a fairly important piece of technical work that has been floating around for a very long time for how you design and implement manifests to combine multiple individual ICN objects into more complex structures called FLIC. I have been sidebarring just now with the author, one of the authors. I'm actually one of the authors as well. And he has actually promised to have a draft of this reissued and out for review well before the November IETF, and we will be able to look at it then and perhaps finally last call it. So with that ado, we are ready to start the presentations. And I think it's Jeremiah who is up first. Stop slides. Some of our talks are remote today, some are in person, so we'll have a mix.
Good afternoon where you are. This is, I'm Jeremiah Davis. I'm going to be presenting ICN Scion, which is a project that we're working on together at the University of Kentucky. Today, I hope to be able to give you an overview of ICN Scion, talk about some of the motivations behind the project, give some necessary background in two non-ICN technologies that are closely integral part of this project, Scion and Rhine, and that to talk about our initial design status and hopefully have time for a takeaway and some questions and answers. ICN Scion connects Indian CCNX autonomous systems. So this is for the Indian CCNX sort of family of ICN ASs to one another via the Scion inter-domain architecture. Our goal is to create a global network service that has qualities that we find desirable in ICN inter-domain attempts that or in an ICN interdomain architecture that we haven't seen in previous attempts. Among our goals, but not limited to these, are the compatibility with the existing internet provider customer model and also the incentive model of the current internet. We hope that our system will not require a global root of trust, and we have designed the system with this in mind. And the end result is that we would like to see an architecture that's scalable and secure. A sort of nutshell overview of ICN Scion. You can see that this is a small internetwork consisting of two ISDs. We'll talk about what those are, but they are essentially groupings of autonomous systems. And if a consumer in AS102 issues an interest that can't be satisfied within AS102, the AS's own ICN Scion components that I'll describe later in the talk determine that there's a producer advertising this prefix in AS4. The border router of AS102 encapsulates the interest in a Scion packet, and then it's tunneled across the Scion internetwork through AS394, AS66, and AS95. When it reaches AS4, it's decapsulated and forwarded via the normal ICN means. If the producer in AS4 is able to return a data object, it is returned initially via the ICN breadcrumb path, then encapsulated again and tunneled back across the Scion network. Scion and ICN are mutually beneficial. And in particular, Scion systematizes inter-domain trust in a way that no previous ICN interdomain proposals have. But it also still, by default, depends on IP at the intra-domain level with attendant security problems such as reflection-based attacks. ICN Scion, our own project, includes producer verification as a step that precedes the advertisement of a prefix in the routing system. This mitigates congestion and cache poisoning, but it also opens up the possibility of a multi-tiered service model where some customers may not be producers with permanent names, but only consumers. Today, we know how today's internet developed, and CIAN and ICN mutually enforce one another's ground-up approach to the redesign of that global internet work on the basis of how we actually use the internet. Our ICN-CIAN project will provide a proof of concept for a network layer that has trust and security as its key design element, that's not a tacked-on enhancement or feature. So what is CIAN? CIAN is a secure replacement for BGP at its heart, and it originates with Adrian Perig's group at ETH Zurich. It combines a security-first approach that doesn't seek to revolutionize the provider-customer ecosystem. So inter-domain packets in CIAN are source routed. They contain in the packet header the attested authenticated paths between ASs, and CIAN is in real-world use in the Swiss banking system, and it's being commercially developed by Anapaya. CIAN ASs, or autonomous systems, are organized into isolation domains, or ISDs. And you can think of this as being similar to an ISP customer core, except for the fact that normally an ISD doesn't involve just one ISP. It'll have multiple ISPs. The actual boundaries of an ISD typically correspond to real-world trust boundaries, like nation states, where the contracts between the ASs can be enforced. The trust that exists within an ISD is systematized in a trusted root configuration. It includes certificate authority keys for the path attestation, as well as various metadata. And within an ISD, there are certain ASs that are called core ASs, and the core ASs are responsible for beginning the path beaconing, which builds paths, which I'll describe in a moment. And they're also responsible for connecting to ASs and other ISDs. The CIAN control plane is shown here, and the key part of this is how paths are built. Core ASs send out beacons that propagate away from the core. They propagate down the provider customer chain. They also propagate to other core ASs, including those that are in other ISDs. And this builds path segments as the beacons traverse the ASs. And when a beacon reaches an AS, it can make a decision as to whether or not to advertise that path segment according to policy down its own provider chain. This process results in authenticated segments that are also oriented. So for instance, we have down segments that are down a provider customer chain, such as M to R. We have core segments that are between core ASs in the same ISD or in separate ISDs, such as C to A in the first case, or B to I to L in the second example, as well as up segments such as F to E to C. So when sending a packet across the CIAN internetwork, remember that I said that CIAN is source routed, so the packets carry the complete path that's made up of two or three of these segment types. An up segment, an optional core segment is necessary, and a down segment. And there also are peering links, but I'm going to omit this for simplicity for this illustration. So suppose that an application in H needs to communicate with an application in Q, with a server in Q perhaps. H will query the CIAN control service, which returns a set of path segments that are known to exist between H and Q. And then the application assembles a path according to whatever its internal application heuristics are for assembling that path. And this path is stored in the ICN packet, or in the CIAN packet header, rather. So in this case, we see H to G to B is the up segment, B to I to J is the core segment, B to I to L is the core segment, and then L to P to Q is the down segment. And the paths are reversible, so this can be used to send the packet back across the network. The key component of our ICN Scion, key components of our ICN Scion design are a gateway that is responsible for name service and Scion control queries. I'll talk about the name service in just a moment. This allows for ICN applications that are unaware of Scion at all to be used in this ICN Scion infrastructure. The next component is the RHINE name service, which is an improvement upon DNSSEC and is closely associated with Scion. Scion border routers, ICN Scion border routers speak both protocols, and they're responsible for encapsulating outgoing interest in data and decapsulating incoming ICN packets. Reflexive forwarding, which I'll describe in a moment, is an enhancement at ICN that enables the gateway to set up interdomain state in the routers. And in ICN Scion, before advertisement in the routing system, producers prove that they can publish under a prefix in a particular trust context that is permitted by the AS. And by default, this is a DNS-like namespace where prefixes are delegated within RHINE itself. RHINE is a secure replacement for DNS and DNSSEC that we use as the name resolution service. It separates securing delegation status from securing zone data, and it allows for multiple roots of trust. We use it both for prefix to AS mappings stored in a special record, as well as to certify the binding between the ICN prefixes and signing keys. And this is very similar to DNSSEC plus DANE. RHINE in particular is desirable because it addresses security holes that exist even in DNSSEC, such as the ability of a compromised parent to interfere in the operations of a delegated zone. And it leverages WebPKI-like CAs, as well as snapshots of the global delegation state in order to prevent this and similar types of security problems. As I said, our system uses reflexive forwarding as a key component. Reflexive forwarding is, as I said, an enhancement to ICN that allows our gateways to communicate state to the border routers. But more generally, reflexive forwarding allows consumers to issue special trigger interests to establish temporary forwarder state between themselves and some producer. And this temporary prefix can be used by the producer to send back reflexive interests, which allows for multi-exchange handshakes without resorting to interest payloads, which we consider to be undesirable, or permanent advertised names from the producer. This is a top-down look. It looks like some of the lines might have gotten messed up in the conversion to PDF, but this is a top-down look at a Scion AS, and what this is intended to show, if the lines were more correct, is that the default routes are always towards the logically centralized ICN Scion gateway. In a real AS, there would be more than one node that was running the gateway, but in this case, we have them all together. The default routes for all unsatisfiable interests are directed towards this logically centralized ICN Scion gateway, and it can determine through the RHINE and Scion control service lookups if there's a remote producer for the data and the interdomain path to that AS if it exists. It can then, the gateway then communicates this information to the border router that's on the first hop of the Scion path, and the router encapsulates the interest. If it receives return data, it begins to advertise the name of that data or the prefix of that data directly, so that future communications can bypass the gateway. This is a little bit more information about locating data with RHINE. I'm not going to go through the whole thing, but the key thing to take away is that the division of labor that exists between the gateway, which is responsible for name resolution and control service queries, and the border routers themselves, which simply encapsulate, decapsulate, and eventually begin to advertise the remote names. Here is a brief example say that we have in our local AS, there's a consumer that issues a interest for a name that finds no match in a FIB. It's going to be forwarded to the ICN Scion gateway. The gateway then uses the RHINE lookup to obtain ASs that have sources for the name prefix. Actually, that really this should say name dot prefix rather than simply name. And in this case, it finds both AS4 and AS9, and it makes a decision based on AS policy or some other information that it has about these two ASs and decides on AS4. Then the gateway queries the Scion control service or path service, and this results in a set of segments, of path segments that can be assembled into path 1 or path 2. In this case, the gateway chooses path 1, and then it uses the reflexive forwarding enabled exchange to set up state in the border router, associating path 1 with a PID entry for that name. The border router then encapsulates the interest as a Scion packet, forwards it along path 1, and when the Scion packet reaches the remote AS4, it decapsulates the interest, forwards it via normal ICN means to the producer. And if the producer returns data, that data is returned back along the ICN reverse breadcrumb path and then tunneled back across the Scion internetwork. When the data packet returns to the originating AS, the data packet is decapsulized, it's matched to a PIT entry and forwarded back initially to the gateway, which then forwards it back to the original consumer. If after one of these successful interest data exchanges on a particular prefix, the border router eventually begins to advertise the availability of the name prefix in the ICN intra-domain routing system. Today, we have the separate components of ICN Scion working in the fabric infrastructure for network development and testing. We're using the C4 implementation of CCNX, though we are designing everything in mind for future use with NDN as well. And we're trying to make as few changes to both Scion and to the underlying ICN technologies as possible. But we have C4, Scion's open source implementation and RHINE's open source implementation running in Fabric. And so now we are in active development of both the gateway and the border routers. We also have a means in place for a connection to the Sierra Scion system it's a research network for testing and development. Our future research includes the details of the producer verification protocol that I just barely touched on today, solving the problem of locating RHINE servers without global IP locators, ensuring that the major components of ICN Scion are scalable, and some details of the control space, the control namespace design. Our ultimate goal is an off-the-shelf network layer that combines the best of both ICN and Scion with improvements over the legacy BGP IP internet. And we found that the steps towards getting there, particularly with mature research implementations, aren't straightforward. And we welcome comments and questions. Thank you.
Great. Does anyone have any questions? Oh, we've got a question from Tilman.
Hello, yeah, my name is Tilman Zeschke. I'm from ETH Zurich. Yeah, nice talk. Just one question. So you're using that internet gateway a lot. Have you thought about actually going directly to the clients, or do you need to go through a central gateway?
So yes, that's a good question. So we do think that some of the clients will be Scion aware, and so this will allow them, for instance, to have multipath capabilities with both at the ICN layer and the Scion layer. but the choice of a gateway is for two purposes really. One is to allow ICN applications that are not aware of Scion, so that are purely unaware of location at all, and also it allows for some use of ICN caching if you can have these prefixes advertised more generally from these exchanges.
Okay, thanks. Yeah, that makes sense.
Dirk, let's make these very quick because we're already clocking a little bit over the allocated time.
Dirk Kutscher, hi, this is really great, interesting work. I'm just curious, have you made any performance measurements so far? Because I think you introduced quite a few extra interactions. Just curious.
Yeah, not yet, but this is the part of the summer work, basically.
Okay, thanks.
And Stuart?
Stuttgart, just wondering if you can point me to any drafts or whatever on how you take advantage of any one-way broadcast links.
I'm
worked with Scion in the first place.
Ken, do you have any ideas?
You're asking about leveraging broadcast multicast capabilities for the ICN part?
Yes.
Yeah,
Yes.
so we don't have anything on that at this point. We're focusing on getting just interdomain point-to-point working at this initially.
I saw Ken had a hands up earlier, but I suspect like you're okay then, I guess.
Yeah.
Cool, thank you.
Okay.
All right, next up, we have ICN adaptive in-network computation. If I hit it.
Ket, you're there? Hi. I didn't see you. You might want to move the mic down just a little bit.
Okay.
Yeah. Oh, let me,
Yeah, that should
give her
work.
the.
That should
Did
work,
you
yeah.
give her the clicker?
Yep.
Okay.
I did.
Hello, everyone. My name is
I started the time.
Speak a bit louder.
louder. Okay. Hello, everyone. My name is Ted from ICT Japan. Today, I would like to talk about ICN Enable adapted in-network computation for resilient distributed AI. So let me start my presentation. So as we know that traditionally AI processing are centralized processing, and we have to move all the data towards the centralized server or cloud server for the processing because all the algorithms are inside this cloud or server. So federated learning, in case we already moved this problem by putting all the computation inside the device. So it solves some of the problem, but it still have some central aggregator to aggregate this computation. And although we have like distributed data, so we move to the Edge AI. So Edge AI offer the near source processing. So Edge server can process this kind of like complicated processing, but we still have a static Edge server to move data to the static Edge server. So finally, we have distributed AI. So distributed AI move the algorithms to the data. So we can do like a lot of like autonomous processing for the system processing in more distributed way. So it moved data travel to the compute towards the compute travel to the data. So however, like we have still have key requirements in the distributed AI. We need communication efficient model sharing and real-time responsiveness, and also location independent execution for the large data, and also we need dynamic text allocation. So what makes this problem more confusing is that we have like this day we have a lot of AI-driven applications which have multimodal data inputs, and we still have a lot of large scale data and also very frequent model sharing inside the network. So we need real-time processing across the distributed system. So as we can see that we have a lot of like data from the IoT devices, and also image and video streamings and text data are shared between this distributed network. And also we have limitations such as like this AI complexity makes this computation, large computation will be less scalable. And also we have server-centric limitation. And also, however, like serverless approach offer the flexible computation. However, they still need to struggle with the compute and latency sensitive application for the distributed AI workload. And finally, and most importantly, communication bottlenecks for the frequent AI model sharing. It's still have a lot of like communication bottleneck problem. So as we can see that it's federated learning, as I mentioned earlier, has aggregation problem and also distributed AI system. Currently, we still have tight coupling with the host location. So in here, as we can see that this endpoint-centric communication and computation still lacks in network processing and also excessive data movement between the host and the the sender and the receiver. So we use in here, so ICN offer the very flexible and embed reset reuse for the computational result and coordinator-free computation and AI inference aggregation can be performed. And also ICN offer multi-path and multi-tech model update and distribution. So here, starting from the ICNI, we have like existing work on inner work computation, and as you can see, the NFN name function locate, model compute and trigger inner work computation and execution, and also NFAS also offer the function placement in the dynamic placement and execution by a lightweight kernel and run on any devices. And RISE, as we can see, that it decoupled invocation from the return receiver by using the tag and also no persistent network state. And compute function networking also offer the based on the RISE and distributed edge computing will be offered. However, as we can see, like in the current distributed AI and AI computation needs statefulness because as, for example, we consider some of the vehicle object tracking example. If we only track the data, we don't need the state because, for example, in the frame one, we only need to detect, for example, one person, but we need to track this person, or maybe we predict this person will be going through the road, or maybe it crossed the pedestrian. So we need state, and we need to track this person. So we have to have the resolve the AI function and preserve the contextual state for the dependent text as a named data. So we propose adapted inner-word text for execution for the low latency distributed AI. So in here, like AI function and inference text can be invoked as inner-word services such as object detection and anomaly analysis. And also we we propose two mechanisms. The first one is a request to compute to see model. It treats the intermediate output and computation as a name function. And the second is a state management, how we can track this kind of like AI text by using the contextual state, and intermediate reset can be version as a name object as we are currently working for the versioning draft. So we we want to refer this versioning as a version tag, and we propose this kind of like state management. So we this kind of like AI computation can be fetched from the correct version and result. So it also enables the reuse of the computation and the seamless handover without the recomputation. So as we can see, like first content-aware function execution will be happen for the data. As we can see, the requester can request by using the interest for the text one and D1. As you can see in here, extended extended ICN naming. ICN naming with the versioning V1 and V2 for the statefulness function. So we can use the ICN interest name. For example, for the vehicular object detection, we can use the vehicle text one and version one by embedded the functions and the data here. So version progression will be happen by the producer. So with the sequential counter. And also in the function execution, we have the adapted node selection. So we compute the node that received the interest and confirm its eligibility to compute this function. And this by considering the capacity score and available resources. And also it also minimizes the communication and execution costs. And finally, we compute the node and return the data. And the return data can be cached within the network. So we don't need to compute from the draft or from the beginning. So this computational result can be used by requesting the version. So we can also track the old version and the new. We can also track the new version. So for more complicated case, if we can't find any data or the function in the compute node, so we can also use the adaptive data and function coordination in here. So in the coordination phase, if as we can see, the CN1 has no data, so we need to get adapted function coordination from the data producer, so it can generate the new interest to fetch the data. So from the data producer, it get the data by getting the data result too, and it can be returned to the content like content computation node, and the computation node has all the text and the data by coordinating these data and function together, and then this function can be computed and executed within the network. Then the result will be returned as a new data object, and also it can also cache in the network. So this is the more complicated case for the missing data and the function like coordination within the network. So we perform various evaluation using this PICN, open source Python ICN framework, and we use the image for the text we use the image-based project detection using the YOLO 3, YOLO 5, and YOLO 7 model, and we use a nuisance data set for the object detection model, and also each data object has 180 kilobyte, and we set up the communication delay for 2 milliseconds and bandwidth for 10 megabyte per second, and we use this evaluation topology with 13 node with the BA topology, with including the 5 register, 10 data producer, 3 compute nodes, and 12 ICN router. And we have like some various results. The first one is average inference latency. So we check our proposal can offer like how we can offer the inference latency for each of the various data set and the various models. So YOLO 3 and 5 and 7, we offer our proposal can support multiple model complexity with the low latency, and also low for the figure B, we have like low computational text execution compared to the cloud and edge, and also it is very competitive to the local execution. And also for the figure C, as we can see, as the numbers of text execution increase, we have the improve the inference throughput in here. So from this slide, as we can see, by using ICN, we can have latency-aware text placement in the network, and which is very practical for the scalable and responsive distributed AI services. And next series of like evaluation is that the figure D show the text success rate. As you can see, within the 10 millisecond of the threshold, we get over 96.6% of the packet of the text success rate, with the packet loss ratio from 0 to 20%. And also compared to the edge and cloud, it's we have the higher text success rate. And in the figure E, we can see that compute accuracy is over 99%, even with the detected object is increased. And also we have, as we can see in the last figure, it showed the object detection on the Arbenz tree as a successful real-time object detection with a high confidence score. And to summarize this slide, we can see that our proposal offered a low latency, reliable detection and other complex condition for which are mostly applicable for the safety critical applications such as traffic monitoring and autonomous vehicle perception systems. For the last one, like we check how packet loss and how it improved the packet loss and availability of the data. So compared to the cloud and edge, we offer very low retransmission pressure on the network. And also in the figure H, as we can see that there are various fault condition case, and we offer the like fault like 5% packet loss, and we offer the very low fault interest by data. So this property can be retrieved from the key resilience advantage. Like we have the state-aware execution, which avoid the redundant transmission and recomputation. And also we offer adapted node selection. It also redirect the text upon the failure. And also ICN multicast forward the bypass this kind of loosey and fault detection, false condition within the network. So it offers the scalable and the high request load in the unreliable environment within the distributed AI services. So to summarize it, we propose the adapted in-network test execution for DI services, which require low latency, intelligent, and real-time services. And the design proposed the dynamic resolution and fetching of the named data by using ICN, and also we propose a contextual state management to preserve the intermediate data and computation result using the versioning inside the name. And also we offer the seamless function handover, faster recovery, and efficient reuse of the period computations. And the evaluation offer like low latency test coordination with a minimal inference latency and text success rate. So for the future direction, we aim to include the adapted function placement based on the network network workload and the network patterns. And also we aim to include predictive task scheduling using the workload patterns and network dynamics. So these will be the future work. And also we have some publication in the Globcon and the Infocom. So it also include verification using this data-centric protocol. So if you are interested, please check out our paper. And that's all. And thank you very much.
Thank you. Do we have any questions? Oh, Dave.
So one of the nice things we get out of this is the ability to cache results and not redo computations when multiple people ask for the same thing. For this particular application, either training or inference, where do you expect to see that happening? When I think about it, I think every one of the computations is going to be slightly different from the other one. So do you see opportunities in which we can avoid the repeat computation and actually use cached results?
I see that, because we have the most obvious use case should be the vehicle detection. For example, there will be for example, in 10 cars near the pedestrian or the traffic light, we can see the same, we can have the same data object detection, and we can have the capture can be captured the same scenes. So if in this kind of autonomous system, if they have the same scene and they need object detection, for example, there's 10 people near the pedestrian, for example, we have the traffic light is already red, this kind of thing. So in this kind of use case, we can imagine to use this kind of recomputation will not be required for the nearby cars and vehicles.
Lovely, thank you.
Thank you very much.
Any other questions?
Thank you.
Can you make sure to add yourself to the queue so that it's easier for the note takers to
how
keep
does
track
your
of it?
system discover eligible computer functions when service availability change dramatically or connective is intermediate?
Yeah, so in this slide, we show the node selection in here. Maybe I think you are asking for this kind of adapted node selection. So we have compute node, for example, we have compute node 1 and 2. Then we compare this kind of optimal compute node capacity using the capacity score and available resource nearby the compute node. For example, we have roadside unit near the pedestrian or near the traffic light. If we have 2 or 3 roadside unit, we share all the resources and we compute within these 3 roadside units, and we choose the optimal node, compute node that can be compute this kind of function and this kind of computation.
Okay, thank you.
Thank you.
Lovely, thank you so much. Let's get the next one going.
Stop control. Yep, there we go.
Yeah.
Stop slides.
So up next,
Thank you very much.
I think it's Leisha. Yes.
I'm ready. How do I drive the slides?
We're going to pass you the clicker. Just give you a minute.
That should be you now.
You should have slide control, Leisha.
Okay, great. Hi, everyone. Unfortunately, I wasn't able to make it to Vienna, so I'd like to do this talk remotely. For people who attended the Indian community meeting this year, back in May, you have heard the talk of the same title. This one largely is the same, but I think I clarified some basic points. Let's get into it. The question is why, after so many years, we revisit routing scalability question again. I remember Tony Lee and I co-chaired routing research group. That was in the 2007 or 8, around that time period. So here's why. It's highly related to named data networking. We all know routing scalability is a research challenge from day one. In the early days, in the late 80s, we worried about routing scalability. I don't know if Bob Hendon was in the room. He actually chaired kind of a private group looking into that question in the 80s. Now, NDN, ICN, we propose to use data names for network delivery. That's, it looks like just magnified the scalability problem by orders of magnitude. So this talk, we take a historical view on the root cause of scalability. And most interestingly, we notice that there's recurrent patterns on those scalable solutions. So we want to extract out the common pattern and apply the lessons learned to the future routing and the forwarding system designs. So what's the problem? I think people who ever cared about routing know this issue. There's a direct conflict between the end systems and the network. The network wants all the IP addresses to be assigned by providers so that it has a topological meaning and can be aggregated by prefixes. On the other hand, the end users or end enterprises systems, they really want stable identifiers of the endpoints. Everyone, I believe, has changed the providers from time to time, and yet they don't want to change addresses. Then you can see that there's a direct conflict. And that led to this very famous Rector's law. Addressing can follow topology, or topology can follow addressing, choose one. That is seemingly like an unsolvable problem. Is that really so? So we turn this thing as the following. I think on the left side, it's really logical identifiers. On the right side, it's a topological identifiers. Instead of declare the conflict never resolvable, we actually notice that there's a number of solutions that has come out over decades that actually resolved this conflict via mapping. I will just mention the most noticeable ones over the history. So the very first one is really mapping in CAP. It's the RFC 1955. I think it's published in 1996, I believe, by Bob Hendon. It essentially proposes the idea to say that we know that there's end identifiers, and then there's a so-called locators, which is the topology-based address assignment. So we resolve the conflict by mapping the identifier to a topological address at the ingress into the network. So therefore, inside of a network, you only see the topology-based addresses that will scale the routing. So that's what I indicated here. You only see the locator-based address, and when you are exiting the network, the egress router going to remove this encapsulation. So the end sites always work with their desired stable addresses, and the middle always work with the topological-based addresses. So everyone is happy. Now, how come this good idea never got actually adopted? So there's challenges there, right? So let's take a look of Lisp as a specific attempt to actually realizing the idea Bob Hendon put into the RFC 1955. So Lisp is a locator identifier separation protocol. That's precisely the point. So what Lisp proposed is just like they call the EID is the RLOG, which is topology identifier. And then they provide the mapping table called this dedicated database tree, maps the locator, maps the EID to RLogs. And it will do exactly the same encapsulation, decapsulation, like in Bob Hendon's RFC. But that, got published as an experimental RFC in 2013, and then became a standard, actually. I didn't realize that until I checked. Standard in 2022. But look at the current deployment. I believe there are places that actually use this. But by and large, I would bet that many people at the IETF haven't paid attention to this thing called Lisp. Where is the hangout? That is on the DDT stuff. So you can provide this mapping system. The question is, what is the governance rule for this mapping system? Who's going to provide this? Are we going to do a kind of a second copy of DNS equivalent? And that is really unresolved issue. So Lisp, I would say that nice idea, but the intrinsic barriers that stop it from wide adoption. Now, what actually get adopted to scale the routing is MPLS. People may not think of MPLS as a map and encap, but that's exactly what it is. As the ingress router into a big ISP's network, you actually map this forwarding equivalent class, FEC, into the MPLS label. So therefore, instead of the core AS, that one AS, you really route on the labels. And the label, of course, are assigned by the network operators, totally under their control, is totally scalable. It's the topological identifier. And then again, at the egress, of course, you exit the current AS, move on to the next one, and then you go back to the original prefixes again. So you can think of MPLS as encapsulation. It's not like IP in IP encapsulation. It's layer 2.5 encapsulation. Nevertheless, it achieved exactly the same goal. And this picture looks exactly the same as I showed you for the original Bob Hendon RFC. Now, that's about unicast. How about multicast? We all know this IP multicast forwarding approach developed by Steve Duran back in the late 80s. Later, there's all kind of different realization. For people old enough with the IETF, you could recall the Unbound deployment in the mid-90s, where it was the first time IETF meeting got broadcast out for the remote participants. I hate to inject historical anecdotes into this. I remember so clearly. My dear friends, Alison Mankin was pregnant, couldn't attend the meeting, and therefore she's asking, hey, we have all this audio and video on IP now. That's the leak and the byte, and also the IP multicast. Can't we distribute IETF meetings for remote participants? And that's how the Unbound actually got started, and people tried it out. I really love that idea. Ideas are lovely. The question is scalability. So at that time, Duran's configuration is that the source and then the group address. And therefore, every router, generally speaking, needs to keep this ICNRG state, that is per source group address combination. And then you can think of how well that scales. The number of groups are now bounded. Well, you may say it's bounded by the class D addresses. Yes, that's 2 to the 24, but the sender per group is still can be a very large number for large groups. We just put a very simple explanation here to say that it's really much worse than unicast conflict. So as multicast get deployed, here and there, maybe like a Lisp, right? But those are very engineered solutions. Single source multicast and for specific domains and specific usages, it's like IPTV. But fundamentally, this scaling issue, I think, confines the multicast deployment. Now, since late 2010s, I think this beer thing get standardized there. I put it here, 2017. This actually took an entirely different approach to multicast forwarding. I think people here should be aware of the situation, how it works. What's new on this slide is to take a different view on beer. So for beer, you have the ingress of the AS. I forgot to mention that for the MPLS mapping cap, the fundamental question, how the map gets provided. If I go back, can I go back? Can I go? Oh, I can go back. Where is it? So the map is provided by IBGP. IBGP says that, okay, for this exit router, that's all the destinations you can reach. So map is actually a very important thing. Remember, I mentioned that Lisp get kind of challenges with how you provide the mapping information. And then for multicast, how the mapping is done. So for the beer inside of AS, there's also the IBGP provides the information to say that at each egress router with an IP address that has membership into it. So therefore, the ingress router will just put this bit string onto the packet. Then inside of the core, again, packets get forwarded based on the bit string. So you can see that it goes to the exit router. Every router actually splits the bit string so that packet flows down along the tree to reach individual receivers, say this way. So therefore, if we call it mapping cap, where the map happens at the ingress. Where's the in-cap? In-cap actually is just like a bit string that plays the same role as the unicast encapsulation because each bit tells the router where to forward. Just like the unicast encapsulation, the outer address tells the router where to forward the packet. So that's we think is the equivalent. We call beer is a multicast mapping cap. Therefore, you can see the scaling issues. For the unicast, that we still deal with PGP, and that is still proportional to the number of prefixes that's out of the network's control. So IP multicast, the similar situation getting worse because the ICNRG combination gets way, way bigger. Then for MPLS, inside of domain, they do mapping cap, so it's beer. Now, we just put this in this time scale. You can see that mapping cap developed in the 90s, and in the 2000 there's MPLS, and then later there's please forget the standardized, and then we have beer for multicast again. The one thing I just put a note there, that is across the domain, we still deal with the poor prefixes. The reason is that although we have ASs, AS is not a routing unit. You don't have a forwarding table to say for AS, say 3336. I think that used to be the level 3 address, level 3 IP number. You cannot route to AS. AS merely is like a logical unit that controls the BGP prefix reachability propagation as a policy onto it. And therefore, for both unicast and also multicast cross boundaries, you're still dealing with address prefixes. Now, the AS as routable unit. This is my last slide. I think we can draw 3 licenses. That is, if you want to scale routing and forwarding, you have to make it work with the topology and not the external logical identities. You like this source-specific multicast. This kind of you just have those overhead deferred to elsewhere. SSM requires configuration and limited to within specific application domains. And then using mapping cap is really the right way to resolve the conflict between logical and the topological identifiers so that you can scale the forwarding and the routing based on the topology and not external factors. And our observation especially pointed out is the third point, that is that the mapping system is a very critical ingredient in the future scalable routing and forwarding designs. As we can see that IPGP, that was part of a BGP, so it provides the mapping for the MPLS and also for their within AS deployment. But like Lisp, and also I would add ILNT, they will try to add a mapping system to an existing deployed topology. And so far, we have not seen widely successful approach based on this post-factor add-on of the mapping system. So that's the end of my talk.
Thank you. Thank you, Alicia. We a little short on time, so I want to get right to the questions. Please put yourself in the queue if you have a question. I think we have Ken first in the queue.
Hi, Alicia. Thanks. Nice talk. I'm wondering how you feel about Scion as an instantiation of mapping and cap, which actually allows you to route to an AS based on AS number.
Yes, Scion, I did that. Unfortunately, I missed a little early today, so I didn't hear the full Scion talk. I think for Scion, I have different comments. Maybe it's not related to mapping and cap. Shall I reserve that for a later email exchange? So I don't divert.
Sure, that's
the
fine.
The mapping and cap is a way to scale routing and forwarding.
Good. Roland, you're up next.
Yeah, Roland, hi. I just want to mention that there are actually schemes that support ID-based addresses without any ID to locator mapping. So I put a reference to Kira into the chat, so you may have a look at that one. So it's a scalable routing scheme that only has logarithmically sized routing tables, and the price is stretched for sure, but it works without any central coordination also. Thanks.
Where's the pointer?
The chat.
In the chat, I didn't see it. Oh, this thing, you mean that's a KIRA? This is a
Kira, yeah.
Well, again, time is short here. I think there's a lot to say about DHT-based routing.
Yeah,
I think there's a paper, routing on floor laughing. It's a ROLF. Do you remember that paper?
Yeah, Ruffle. Yeah, I know. I know.
Right. I think let's start a conversation with that paper, but maybe not here, given the time limit.
Yeah, and if you want to sort of like have try to get a whole map of the space of the approaches, whether you like it or not, hyperbolic routing is another quite scalable approach which trades off stretch against state. So yeah, there are other things, and you may be right that map and NCAP's the only thing that has any hope of succeeding, but maybe we should understand the whole space so we can place it appropriately.
Yes, yeah. So yeah, I should have mentioned that, but I think this echoes my point. Mapping is really a critical point if you want to do mapping in CAD. And so far, we haven't seen very successful post-facto injection of a mapping system. And that's the point. So I want to just say one word about NDN. NDN start from day one. We knew there's a logical versus topological conflict. So in early days, people probably remembered we had this thing called a forwarding hint. that is an interest can carry a forwarding hint, which is the locator, and the name is still the identifier, identifies the data you want to take. But then, where is mapping? In many early examples, we actually have the mapping supported in a kind of case-by-case situation. It's only in the late implementation we realize that actually when we design the new routing protocol for NDN, this NDN DV decent vector NDN routing, we realize that we should have a unified mapping system as a part of the routing. So this is my last comment. Next, let's talk about that.
Great, thank you. This is great discussion. Well, we need to move on because we're trying to keep the time. Kenyan, you're on.
Yeah. So I can control the slides now.
That should be you.
Okay, thank you. Hi everyone, I'm Tianwen. Here we are presenting the work that Leisha mentioned. That is, when we designed the new distance vector routing protocol, we realized that it is the right time to apply the map and in-cap into NDN routing so that we can scale the whole network. We know the context well. That is, as earlier people mentioned, we NDN route packets by names, but obviously we have tons of DNS names, much more than the IP addresses people can have. Especially the situation gets much worse when you consider multicast. For example, the recent application called Only we just developed. If you can create an overleaf-like directory so everyone can collaborate on that, but how you communicate, you must have multicast to synchronize the state, and also others need to fetch the added data you have made. So given these tons of application names, how you scale the routing, you cannot afford an exploded FIP table. So this is the problem that we are actively facing in the end. And as Leisha's talk, that is not the NDN unique problem. Routing scalability is long-lived concern, even for internet from day one. And there's a long-lived identifier locator conflict too. And map and in-cap, both by IETF standards, by research work, or engineering practice, for example, MPLS, although it didn't start with a purpose, but it ended up with the practical answer. That is, we provide a mapping system and we try to encapsulate the packet with the topological identifier for both unicast and multicast. And this work is essentially a map and in-cap implementation for NDN itself. We try to leverage NDN unique feature, for example, the state forwarding plane, the default data multicast, and especially security for efficient and secured mapping replication among all the topological points. And with the mapping, we can do the beer so that we can support stateless multicast, which kind of unsolved the problem for NDN for a long time. So this work is essentially a scalable routing architecture for NDN. Let's say this SRAN. We directly build the mapping on the router themselves, and of course the routers need to synchronize on the mapping table. And for the encapsulation, we utilize the existing, let's say, layer 2.5 protocol for NDNs. Currently, this protocol is essentially used for NDN hop-by-hop fragmentation, but it's extensible. So we extend this LPv2 protocol to support our encapsulation point for the topological identifier. And this work, although we aim big, but we slow start. That is, we start with intra-domain routing that within one routable domain. And the routing protocol has already established at least the router reachability, then how we do map and in-cap within a single routing domain. For map and in-cap at AS level, that's our ongoing work. So that's out of the scope of this talk. Overall, in a routing domain, we consider there are, of course, end applications. They register application prefixes to the client-facing routers or application-facing router or edge routers, whatever you want to call. And the edge routers, they have the mapping table, and they synchronize on mapping table, and they try to, when they receive a raw interest from the end applications, they will try to look at the mapping table to look at, okay, what is the topological endpoint? Which is the topological point I need to route to? Then directly puts that router ID in the encapsulation layer, so that the layer, the router in the middle, say the core routers, the gray routers in the figure, they only forward based on the encapsulation header. They do not need to look at application names. So at least we have a relatively flat forwarding table in network core. And at the end edge routers, we have the mapping table called prefix egress table. Essentially decide for a specific prefix which is the egress router you need to visit to. And we also have the control plane component we call prefix state database. Essentially, all the edge routers, they join a synchronization group and say what are the prefixes attached to me, and is it multicast prefix, unicast prefix, and also as order routing announcement, we have the time to live. For example, how many routers? 6 routers topology. We have the 4 edge routers at the 4 corners, and I have 2 core routers. See, at the router 1, we have a mapping table to say this P4 is available at a topological point R2 and R4. Then when R1 receiving the raw interest coming from the application, it doesn't have the encapsulation header, so it needs to look at the mapping table. And mapping table says R2 and R4 as our destination. Then because routing protocol, the intradomain routing protocols already established router reachability in FIB, so I look at the FIB and say, and FIB says R4 is the closest router. So R1 decide I need to encapsulate this interest with the header R4 to say, so the next router R6 need to know the destination of this interest is R4. So R1 send this interest to R6. And for R6, because it already, the incoming interest already has the encapsulation tag with R4, so it doesn't need to look at the mapping table. They only need to look at the topological table to say R4 is available at my west-facing face, and forward interest toward the R4 direction. And at the exact prefix egress point, we need to do another mapping. That is, R4 need to, as the producer attached point, R4 need to also record for each prefix what are the local faces that I need to send to. So when R4 receiving this face, receiving this interest has the R4 tagged, and me is the R4. So I need to look at the prefix egress table. Then it says, okay, this is the face I need to send to, and R4 can egress this prefix to the applications. And of course, if even you don't have a routing protocol, still, if you only have local forwarder, that means you don't need to look at the FIB anymore, because FIB contains pure router reachability. For pure applications running on single router, say R1, you just look at the prefix egress table. And now, given we have the mapping table, we can talk about how we can extend this mapping so that we can support the beer multicast. So the design decision we made is that we add one more header type to the layer 2.5 incap, that is the beer bit string. Essentially means when the encapsulation header carries the router ID, that means it is a unicast interest. And if the interest carries the beer string, that means it is a multicast interest. And for the ingress router, when it receives the raw interest, it needs to look at the prefix table to say if this interest is multicast or unicast. And if it is for multicast, it needs to look at, say, how can I go back? Yeah, for this case, this P3 is the multicast prefix, and the R1 say I need to send this interest to R2 and R3, and it will construct the beer string to R2 and R3, so that later R5 know how to forward. So yes, this is the example I just talked about. That is, if network providers they assign the beer ID to all the routers, then we can essentially, with the mapping table, we can essentially build stateless multicast. We only keep the prefix application dependent state on the edge routers. After the edge router look at the prefix table, the real internal transit router like R5, they only look at the topological dependent state, which is the beer table, so that R5 knows, okay, the second bit and third bit are set to 1, so that means I need to forward to R2 and R3 and look at its own beer forwarding table to say how to forward R2 and R3. So the entire multicast tree becomes stateless. You don't need to maintain any application state within the network. Now the question here is how we synchronize the mapping table, right? Because after all, one can say routing itself is another piece of application. Then how, if you say application states are kept at the edge, how you can do that? Yes, routing itself is an application, but routing is a special application. So what we have done is that all the routers, they join a synchronized group, and we assume that, and because we assume that all the routers will join the synchronization group, so that, and the intra-domain routing protocol has already established router reachability, so that we can safely include all the routers. We can safely assume that all this multicast prefix /network /PSD/sync, this multicast prefix is available at all the routers that I can find in RIB. Also, for specific mapping updates they made, say /network /PSD, which is the application prefix as a special application, /router / a sequence number which identifies like the mapping table update. This specific application prefix is available at the specific router, which we can find in RIB, so that we don't need to do extra things. All we need to do is make sure that all the routers join the synchronization group, so that we can synchronize the mapping table. And we prototype this routing architecture in the go-on forwarder, so people can, it's already readily usable, so people can use our go forwarder with this map and incap strategy. And because as we said, the routing is merely another application, so of course it need to be secured. So we utilize the existing Indian trust schema enforced policy saying the applications can only announce prefixes that they really own, and the router can only produce its own mapping table data. Router 1 cannot overwrite the mapping table for router 2. And also other like command line interfaces for management. You can manually announce a prefix, withdraw, or register the beer router ID, things like that. For evaluation, to evaluate this work, we focus on 2 points. That is, first, given you place a mapping table within the system and they need to synchronize the mapping table. So an inevitable problem is how we can make sure that it converts fast enough. It is essentially how the sync protocol, the speed of this convergence is essentially the sync convergence speed. So we expect something just like sync convergence. And also, because the ultimate goal is to minimize the forwarding state within the network, so we definitely need to look at table size. And for evaluation, we chose 2 representative topology. The first one is that there's no specific distinguish between the edge and the core. There's more like a more close to the deployment reality of Indian, which means you deploy as overlay, and every single router is application phase, so that you cannot have real core routers. And secondly, it's more like, in theory, you have core routers, you have real application-facing routers, so you can gain the most benefit from this routing architecture.
I would like to remind you that you've only got 5 minutes left, so I suggest you conclude quickly so that we actually have time to discuss.
Okay, sure. So I can look. I can get to the point. Yeah. So the most important thing is, of course, because we kept all the application prefixes on the edge, so we did save a lot of forwarding state in the core. In the core, we only need to maintain the router reachability, and the topology is fixed size. So of course, it stays stable. And for the conventional routing, because you route by prefixes, you can see as the application prefix goes large, you have more and more forwarding state. And at the edge, you can say both the conventional routing and our own routing and our new approach scales linearly with application prefixes. And our next work is to do the map and incap at the interdomain level, because the essence here still stay the same. That is, you have a topological point, and you have logical identifier, and you need to map the logical identifier to the topological point. And AS can be viewed as another topological point. So if we want to do the interdomain map and incap, the first thing is that we really need the AS routing protocol rather than prefix routing protocol, just like BGP. And we also need synchronous mapping between the domains, that is, which prefix matches to which AS. And we also need to solve the interdomain multicast problem, which kind of harder problem for us now, because currently the interdomain beer is not very mature solution yet. So that's our ongoing work, and our ultimate goal is to have the new Indian testbed roll out with this map and incap. Yeah, thank you.
Thank you. Doug, please.
Hi, Tianyan, this is Dirk. Really nice work. So I guess the scaling scalability of the system kind of hinges on the scaling properties of the edge router synchronization. And, so I think you only showed it briefly, but I think you assumed like 64 or 51 edge routers. That's a fairly low number. So can you say a bit more about the expected scaling and also maybe performance latency when you use synchronization protocols like SVS? Not quite sure how well that would work in a reliable scale.
So for the scaling part, because you have to keep all the mapping table at the edge. So at least for the edge routers, they have to have forwarding state. But the point here is that you don't have to, if you really want to optimize, you don't always need to keep all the prefixes in the forwarding table. You can have some on-demand driven. That is, you only put the popular mappings. You only populate the popular mappings into real, like the SRAM or the fast memories. So the whole point is that we want to keep the network itself large state topological bound. For the application part on the edge, I think it's optimizable number. And for the convergence, the number here is that because the existing approach is that you essentially brought new prefix advertisement to the entire network. So actually we are not that. We only add like only 2% of latency, but we save a lot on packet overhead. Because previously you have to broadcast the entire network, but now you exactly multicast the edge router. So the actual saving is on the packet overhead of a new prefix announcement. But also another important gain is that whenever the topological changes, it only affects the routing protocol itself. There's only update in the distant vector protocol. Routing topological changes does not produce like prefix churn for the mapping table, because the mapping table only says for this router what prefixes are available. For internal topological changes, it doesn't care.
Any other questions?
Right, Ken.
Hi, thanks. Just a quick question to clarify. Did I understand correctly that sync interests need to go to every member of the group, so they go to every edge router? Is that what you said?
For sync interest that announce a new mapping table update, it need to get to the old edge routers.
But not for application sync interest, just mapping table update sync.
Right.
Interest.
For application.
Oh, okay.
Yeah,
Okay. Thank you.
That's perfect, right?
Yeah, I got it. Thank you.
Okay, this is my turn. So in my pre-NDN life, we were working on BGP. I think people probably remember that those days we developed some very useful tools. But back to this point, with regarding to the overhead, when we were BGP czar, we noticed two things about overhead on the BGP. One is the routing announcement. That's what we measure. It's a huge amount of shifting. When the ATT and the Horizon has a cut in the middle, in those days, ATT and level 3, then thousands, tens of thousands of prefixes change it out. That's the amount of updates that's overwhelmed the network and cause congestion on their own. So I think what we, doing the mapping in CAP, we separate out the prefix changes from actually topological changes. And that's a big saving based on our previous life with the BGP. The second thing is about routing convergence delay. Because you substantially, by orders of magnitude deduction of the routing updates, the convergence is also fundamentally different. One is that there's not that much volume to ship. Two is that the prefix to router mapping, prefix to router mapping, later prefix to AS mapping, was communicated in an entirely separate channel than the topological updates. So the sync goes really fast because it's not about one router send packets to many others. Instead, it follows the multicast tree. I think Ken's question is a good one as a clarification. We're talking about routing protocol as an application on its own. By protocol stack, BGP is on the IP level. So that's this routing sync has nothing to do with applications whatsoever. It's a really separate sync group. Thank you.
Thanks. Let's move on. Next talk. Give the clicker.
Yep. All right. Take it away.
Yeah. Thank you. Hello, everyone. So my name is Farhat, and I wanted to be this presentation to seek a discussion actually about confidentiality in NDN and how it induced. Thank you. How it induced data-centric confidentiality, the challenges that cryptographic engineers face, and our own proposal to try and enhance the existence. So we know for TCP/IP architectures that we usually rely on securing the channel rather than the content. So utilizing cryptographic channels like TLS sessions. And the main thing to keep in mind here is that the encryption and the security is purely bounded to the session itself. So the security starts, then ends with the session itself. On the other hand, for NDN architecture, we now seek to secure, develop the security mechanisms around the content itself. So first of all, of course, we have that every packet can be signed, and every data packet is mandatory signed at prediction and distribution of it. And maybe the main idea to keep here is that security properties of the data needs to travel with it. So it's either about signature, the key used to sign and to verify the signature, and for our case here, encryption, the ciphertext in itself, of course, and the content needed to, the cryptographic material needed to crypt the ciphertext. A key point here for this discussion is to see that authenticity and integrity are built into NDN. However, confidentiality is left out to the application layer. So we have a lot of work that claim that security is built in natively in NDN, but they usually refer to integrity through the signature scheme rather than confidentiality through the encryption scheme. So when implementing confidentiality in NDN, we are facing a few challenges. Practically all of them comes from how NDN works. First of all, we have the in-network caching, where since the data is scattered in the nodes of the network, and you lose the direct access of its distribution, so you cannot control directly the access to it. Even if you do actually have a direct control on the data, a producer receiving the interest doesn't natively, at least, doesn't know which consumer requests what, since the by default interest packet doesn't hold identity information, and it doesn't know as well how many consumers it will serve. So this kind of makes the key negotiation and key exchange and through channel security practically pointless. And maybe one last thing is to talk about the one-to-many inheritance communication model of NDN, which constitute actually a group key management problem, a struggle, especially when dealing with revocation, where if we want to revoke an access to a consumer. So here we have the data-centric answer, meaning the data-centric confidentiality, where we seek to encrypt the content and not the connection. So the ciphertext, of course, travel with data, and as we said in this previous slide, the security properties travel as well with the packet, which helps guiding the consumer in its decryption flow. One other important thing is to say that access control now becomes a key distribution problem, since now granting access or revoking access, it translates to having or not having a specific key for decryption. So here we take a look at what's maybe a foundational work in data-centric confidentiality, namely here name-based access control, where we solve the key management problem by first of all making the key named data itself and a data packet that consumers and other nodes can request. Also utilizing naming conventions to ensure the decryption flow and automate the key management process. So guiding consumer knowing for content name which key to utilize. Also, if we are working with the attribute-based encryption version of the NAC access control, we now have an access control that fits the one-to-many communication model that we described. Since with attribute-based encryption, we have one encryption that can be sent and decrypted to many consumers. However, here we need to point out to some unsolved points. First of all, we know that NDN supports the decentralized applications, so it only makes sense that the authority here follows this pattern and we avoid this single point of failure. Again, we talk about the group key management problem. Here, if we want to revoke an access in this access control architecture, we are actually ending up waiting for the next rekeying of the encryption scheme, which means changing basically all keys, either private or public, of the asymmetric scheme. And on the other hand, it leads as well to changing the pre-shared, so the shared key that is the symmetric key used for communication, and changing it means inducing another encryption and decryption of participated nodes. So here we are actually going to take a look at each point and discuss them. So first of all, about the centralization problem. Here we can take an example of only the secure decentralized workspace that is built over NDN and that sits on the NDN testbed, and let's take for example, okay, for myself, I'm a user of this application, and I'm connected to the Frankfurt node. So it is my authority, and I want to access the content that is under the UCLA node. So the first question to ask is that who will issue the necessary keys to give access to this other domain data? Is it my own, which has no relation with the data, or is it the authority of the content I want to access, but that doesn't govern my node? Another simpler question maybe is what if the authority, of course, goes down? So we can clearly see here the single point of failure. So how do we revoke access to cache data? Well, answering this is usually about balancing the efficiency of the revocation. Of course, the immediate revocation comes with a cost on the system. Initial solution is to rely on the periodic rekeying of the system to ensure the revocation, either the admission or the exclusion of members in the communication, which means that we need to wait for the next rekeying cycle, which is not an immediate revocation. And if you want to make it more, if you want to apply revocation more frequently, we would have actually to increase the rate of the rekeying, which is of course not without a great cost on the system. So we can imagine the point here on the bottom sliding more through this axis of the cost rather than for the immediate revocation. A more drastic solution for revoking data is to say that for every revocation, I will rekey the entire system, of course, and utilizing re-encryption, because we talk about cache data, and for specific scenarios, we may require that that we control also access to this already cached data. So we actually end up re-encrypting what's inside the NDN routers. Or of course, we will be looking at an in-between solution, so utilizing publicly available cryptographic material to ensure updating the necessary keys, either private or public. And we can also argue that re-encryption is actually two scenario specific. So we may say that a content that is already cached, we only assess the access of consumers when the content is distributed from the producer. So another design choice about implementing the confidentiality. Of course, we may say that each NDN application will implement its own encryption scheme for a greater flexibility, but of course, not really a solution, honestly, because of repeated effort and practically no interoperability between heterogeneous NDN application. To the other way, we can say that we can implement standardize actually confidentiality into NDN, a more drastic solution. So following the signature scheme, which is built in NDN, but of course this risk again of fixing single encryption scheme for all use cases. And again, a middle solution, so working with a security library that sits between the application layer and the network layer. But again, application still needs to use the same library, and it still keeps confidentiality optional in the sense that signature is mandatory, but it keeps the confidentiality to the upper layers. So question here, what's the best approach, of course? So here I will discuss our attempt into enhancing and maybe addressing the points that we've discussed earlier through a security library, a decentralized security library where we utilize multi-authority attribute-based encryption to provide confidentiality in NDN. So for this scheme, we include an immediate revocation mechanism as we talked. So utilizing publicly available information that are shared in the network, and with it an optimization mechanism, because we know that the shared key that is used, we know that it's going to change after revocation. So what we do is that we save cryptographic information done in the initial calculation, and we reuse it in the next encryption and decryption to drastically reduce the cost of it. So this library aims to, of course, to be integrated into existing NDN applications, and it aims to sit between the application and network layer. So quickly here, taking a look at the architecture of the library, which is implemented in a modular way. So first of all, the cryptographic scheme, where we implemented from scratch, in order actually to provide this enhancement and this modification, to provide the revocation mechanism, for example, the optimization mechanism, etc. And other, of course, section, mainly the communication section, which deals with network interaction, of course, of the library, which translates to key exchanges and key management, etc. The library so exposes 3 roles. So for the authority to generate keys, distribute them, and revoke access as well, and of course the encryptor and decryptor role. So to summarize this library, so it aims to provide an open source, decentralized, attribute-based encryption for the NDN community, and of course for who is ever interested about data-centric confidentiality and or cryptography in general, to maybe contribute to and to utilize the work as well. With the library, so we provide as well a benchmark, which you can find within a website. The website is not published yet, but the source code of the website is in the repo, and we make sure to publish the website. So we have the benchmark, the evaluation done on different hardware configurations, where researchers can compare directly their work with it. So that's it. Thank you. Thank you so much. Thank you.
Hello. Go ahead.
I have a question. Have you evaluated the performance overhead of the library resource constrained devices, such as IoT or edge devices?
Could you please repeat the last part of the question?
Have you evaluated the performance overhead of the library resource controlled devices?
Resources? Oh yeah, IoT devices,
yeah.
exactly. So we did on this, actually there is more, the Raspberry as well. So 3 different hardwares where we published it on the website and show for granularity is each cryptographic function. So to encrypt, this is the cost in milliseconds in each hardware configuration. Yes.
Okay, thank you.
Thank you.
Hi, Dave here. So we know that the cost of signing every single packet when you have a large object is quite high. So one of the conventional solutions to that is to use a manifest and amortize the cost of signatures across a manifest. I'm curious how you think that. I mean, this is like future looking, but do you have any ideas about what you think the right way to integrate manifests into the library so that applications can do their interaction with the system based on large objects controlled by manifests, as opposed to having to do the interaction for every single packet?
Actually, in the initial work, we did assume a manifest. There exists a manifest, actually distributed by the producer, to actually keep track of the different keys and content name keys used during a large session of transmission. In our own work, we assume the streaming session, and we utilize manifest actually to keep track of maybe a revocation, but mainly the content name of the keys that need to be decrypted in order to decrypt the data.
All right, Licia, please.
Yeah, first of all, thank you very much. I thought Tianyuan was first. Anyway, thank you for doing this work. It's great. I wish you had we interconnected better earlier so that we can have more exchanges. I just forwarded the NTN technical report that also shared your view about this security layer between the application and the transport or lower layers. I think we share the similar idea there. Regarding using manifest for large amount of small data, we actually have a recent publication on that. I looked from my website. Unfortunately, that hasn't been updated yet, but I'll send you the pointer afterwards. That is actually work done mostly by University of Memphis. They use NDN to disseminate mobile health data. So there's large numbers, small size for data, and they have a very nice way to apply manifest on that. I think Tianyuan has something else to add. That's about our latest encryption progress. But I will let Tianyuan to measure that.
Yeah. Oh, thank you. So I have one other question. That is because I'm speaking on behalf of both only developer and a testbed maintainer. So I thought earlier that you have a size regarding only and its relation with testbed. Could you revisit that a bit?
Yes, of course. This?
Yeah. So what do you mean by my authority goes down? I'm just curious. I didn't quite get. Sorry.
Actually, we'll be talking about governance. So I'm connected. I'm under the governance of an authority, PKI architecture. So I have an authority that distributes me the necessary keys. But when I'm trying to access content that is different from my domain, which means that the producer that produces the content is under the authority of another domain. So here we have a governance problem where the producer and the consumer are under the authority of different authorities. So, and when trying to resolve this solution, one initial idea, of course, is to create a central authority between them, so which manage both domains. But of course, it brings other mainly governance problem in this case.
I see. I think because we didn't sell our application that frequently, so I want to mention there are two important updates in recent only. That is, first, now our application security is completely orthogonal to the infrastructure security. Now, what it show on the right side of the slides, the testbed is only use it at traffic transit. It does not meddling with the application as security. Now only is using pure self-controlled trust domains, trust anchored data. So there's for now only we don't directly get keys from say UCLA node. It's completely to the workspace creator itself. And second is that I don't know if you are aware of the recent trend of, especially in IETF about the message layer security. Essentially, the latest trend of doing the group encryption, and only now is also supporting that. That is, whenever the membership changes, it automatically rotates the keys back some crypto games. So we don't have to face the revocation problem. Yeah, it's facing a different problem now. We don't need to revoke group keys anymore because keys are automatically rotated and is natively have forward secrecy. Just I know it's based on the earlier work, but I just want to share the news.
Well, if I might answer this. So when we define group communication, so we have a content that we have a lot of consumers that shares the same key, right? So it shares the same key. When admitting a new consumer or excluding an existing consumer, and if we are still using this hybrid encryption scheme, so using isometric and symmetric key, we'll have to change the symmetric key that is used in the communication. And of course, here I pull up this NDN application just for example, for a scenario example, for communication example, to showcase the need or no need of central or decentralized authorities.
Tia, you want to say something, or?
I think, yeah, what I want to say is the latest trend is that there's no group key per se. The latest trend, as I can tell, at least in IETF, is that for group communication, you will use this message layer security. And whenever membership changes, essentially you have a tree of keys. And when the membership changes, because when the membership changes, the root of the tree changes, and that automatically rotate the keys by some ratchet scheme. And
I would say shorten the explanation. So the latest, only release actually adopted the IETF standard, MLS, message layer security. That essentially, it's a developed solution. We just use it. That changes the encryption key every time the membership change. And also you can have event triggered, other than membership change, other event triggered key updates. It's all built in. We just benefit from it.
So that we don't need to explicitly revoke the keys.
Right. So we can look at the MLS RC. I forgot which one is it. This is standardized just not too long ago.
I think in the interest of time, I think we should take the discussion further at the mailing list. But thank you very much.
Do something in a few minutes.
All right. Do you think you can get this done in 3 minutes? Okay. All right. We have one more talk that is proposing. Sorry, I'm trying to control two. I'm trying to do two things at once. So we have a proposal from Liu. It's a draft, I think.
Okay, thank you.
Hang on. I need to give control. Misha, I'm going to mute you if that's okay.
Okay. Good afternoon, everyone. I'm Shirley from Nanjing University. Today, I will present our draft on name-based computer service discover for space, terrestrial, maritime, and networks. The key question is how to discover service and reusable result by stable names, not temporary endpoints. Conventional endpoint discover work when the endpoint is stable. In our scenario, this assumption is weak. Maritime gateways, RU satellites, and terrestrial sets may provide changing service, instant or temporary catches resource. So endpoint only discover is fragile. Discover should also describe what is available, whether it is valid, and whether it can be trusted and reused. We consider maritime, non-terrestrial, and terrestrial end domains, include gateways, satellites, end sets, catchers, and result stories. The discover function is logical, not necessarily centralized, because connective may be intermediately catch or exchange. Record must carry that source, age, and validity. This draft focuses for objects, service name, service instance, data objects, and result objects. Our service name give stable identity. Our service instance result at a site. A data object may be input model and or configuration result object is a reusable output. Discover record bind these objects with metadata, capability, validity, policy, and trust information. The draft define requirement only. The draft discusses for use case, maritime analysis, optimistic satellite access, catches result reuse, and operation during partition. Together, they show that Discover must support intermediate connectively cross-domain policy and safe result reuse. The first requirements group is stable naming and capability description. Service name should remain stable when instance move restart, or replicated service record should describe capability versus and dramatic method with time stamps and validity provide. The second group is description awareness and result reuse. Record needs need explicit validity and record should not provide current recursability. For reuse, result must be bound to service identity warrants, input data, parent, and exclusion context. The third group is trust, authorization, and development. Discover record must be integrated, protected, and attributed to authorized publisher. Cross-domain trust must be explicit. For development, the design should work with existing API network. Native ICN forwarding should not be required everywhere. This draft is related to ICN, DNS-SD, CATS, and DTN. DTN-SD supports service instance discover, but lacks fully validity, provenance, and result reuse semantic. CATS focuses on traffic stream, while this draft focuses on discover method before stream decisions. Let me conclude. Cross-domain system need to discover beyond endpoint lookup. Discover should separate stable service name from temporary exclusion logicals. Record should carry capability, validity, for instance, provenance, and policy information. Reusable results are useful only when reuse conditions are verifiable. Open questions remain on record format, trust, reuse policy, and integration with CATS, ICN, or DTN mechanisms. Thank you. We are coming. Welcome.
So given the time, I'd like people who've looked at this to take comments onto the list, and we can continue the discussion there. So thank you very much.
Thank you. Thank you.
So let's just wrap up. The one thing I want to cover right here, and we'll also post the list on this, is that the good news is that we had a tremendous amount of interest in interacting in person and, of course, remotely at this IETF. So there's a continuing interest in this research area. And we had more talks than we could accommodate even in the 2-hour session when, of course, given the constraints of scheduling at the IETF, it was actually quite difficult to get a 2-hour session. We wanted this to have a less time than that. So given this, I'd like to get feedback from the community as to whether it might be a good idea to have an earlier meeting before the San Francisco meeting in November. where we can accommodate some of the talks that we postponed out of this meeting, couldn't accommodate, and also maybe to get started on some work, particularly around Flick and the versioning draft that's in process and other things like that, so that we're not sort of like piling everything up at the last minute before San Francisco. So I'm going to post to the list what people think about the advisability of perhaps scheduling an interim meeting. It would probably be mid to late September, so we split the time, and people are back from vacation, and for, academic folks are back on campus. It would be obviously an all online meeting, not an in-person meeting. So look for that on the list, please, and please weigh in on whether you'd like to A, have the meeting, and B, if you have a talk or a topic that you'd like to discuss at the meeting, propose that so we can put the agenda together well in advance. We are just about out of time. I'll remind folks that we do plan to meet again in person in San Francisco. I don't know which of the chairs are actually going to be there in person. We'll manage one way or the other to make that happen. So also give some thought to what we would like to have happen there. Dirk, do you have anything to add? Great. So thank you, everybody, and off to the plenary. Oh, pleasure. Yes, thank you.